Now, one of the important questions you can ask is, what is astronomy? And you have a definition on the top and also on the lecture notes. Perhaps the simplest way to say it is if you consider here the Earth, right? This is where we live all our lives for hundreds of years, thousands of years. If we think about the Earth, astronomy is essentially everything else. Everything that we study beyond the Earth is the realm of astronomy, anything beyond the Earth's atmosphere. So it means that even for the largest scales that typically we associate with, okay, you're doing cosmology, it is still really astronomy. And the differences between astronomy, astrophysics, and cosmology can be very blurred and can be open to interpretation. But really, astronomy deals with anything beyond the Earth's atmosphere. And for a long time, we thought that the universe looked just like this, that we were in the center of the universe and everything would revolve around the planet Earth, including the sun. So this is the geocentric view that was accepted for a very, very long time. And that meant that the limit of the universe was essentially this part made of stationary stars, some sort of sphere where stars would be fixed, and that sphere would rotate also around the Earth. Now, it turns out that even in the very, very good old days, where we were the center of the universe, and the universe was pretty much just at least part of the solar system, we were already quite insignificant. I mean, the volume contained in the geocentric universe is already quite big when compared to us. And something you can find in your lecture notes in section 2.3.1, when we start talking about how we can measure distances in the universe, is to quantify our cosmic insignificance. Here in 263, I'm defining cosmic insignificance essentially as the ratio, and you can see it here, the ratio between the volume contained by a human, and we're going to use spherical humans, but the volume should be relatively the same, regardless of what you actually do. And if you think of a spherical human or a normal average human, the volume contained within me or someone else is something like 10 to the minus 10 cubic kilometers. And the volume of the universe, even when it was just this, right? Just the geocentric universe where the Earth was at the center, and it was just not even the full solar system, but just essentially up to Saturn and then this firmament of fixed stars, the volume was already something around this order, 1 times 10 to the 34 cubic kilometers, which means that if you're calculating our cosmic insignificance right here and you divide the volume of a spherical human by the spherical universe, you get a very small number. This is 7 times 10 to the minus 45. And these were the kind of really, really good old days. So things only got worse. And just to point out that here I'm assuming that the radius is essentially the radius of the solar system. That's 150 times 10 to the 9 kilometers before I do a spherical approximation. And you can do this as well. And we're actually going to update this number when we look at the full galaxy and when we look at the full universe. The bottom line is that even in the good old days, we were just a number, we were 1 in a number made of 45 zeros. This was how cosmically insignificant we were already, even back then. Now, moving into what's really core in astronomy, or at least part of it, which is measuring distances. Traditionally, if we could not go out nor have really fancy, sophisticated instruments, one of the first things we would have to do is to calibrate distances on smaller scales. So measuring the size of the Earth was fundamental. And as you'll see in the lecture notes, even back then, more than 2,000 years ago, people already knew that the Earth was not flat. And specifically, Eratosthenes, or however you can pronounce his name, was actually able to make a very simple experiment. You might find this in many textbooks and also in at least Carl Sagan's Cosmos series. So let's go to the simple illustration over here. So this is the Earth where I'm standing. And what Eratosthenes actually realized is that at noon, at summer solstice, he knew that essentially the sun would hit this well. This means that it would be hitting it at 90 degrees. So you could imagine that on one year you make this discovery. So because he actually went quite far, so almost 800 kilometers, and back then there were no airplanes, you would think that what you do is next year, at that time, at that date, you're actually somewhere else where you know the distance very, very well to, in this case, Cn, and you actually measure the angle of the shadow of the sun. So this angle, that in this case is x, will essentially be to 360, the same way that the distance you see here will be to the full circumference of the Earth. And this very simple statement is what is expressed here. And this allows you, if you measure x, which is the angle, and d, which is the distance between the two points you're doing, it allows you to calculate the full circumference of the Earth. In this case, the angle was something like 7.2 degrees, which leads to a circumference of 39,350 kilometers. With very simple maths and realizing that the circumference divided by the diameter of a circle is pi, you can actually figure out what is the diameter of the non-flat Earth. And it's actually quite impressive that the value that the Greek guy got almost 2,000 years ago is really close to the real value. So it was just off by 2%. So this is really quite impressive. And this measurement is already really interesting because it tells us about how big our planet is, but it becomes even more important and interesting because it can be essentially one of the starting points towards measuring larger distances. If we know the size of the Earth, the other thing that we can start to look at is to compare the size of the Earth with the Moon. And once we know the sizes and distances of the Earth and the Moon, if we actually look at special positions between the Earth, the Moon, and the Sun, we can, as I'll show you, determine the distance from the Earth to the Sun without ever getting out of the Earth, and also even without using any fancy methods that we do now.